see, we have calculated the error, okay, because we have already calculated using the forward propagation what is the output 1 and what is the output 2. Now we have two expected outputs, okay. So expected output for y1, which we call expected output 1 is 0.05, and output 2 is expected output is 0.95. You can see that these are probabilities, so if we add them up it will become 1, right? So if the output 2 is probability 0.95, that means this is like higher probability or expected more that this is the final outcome, okay. So the neural network will choose this as the outcome. Now you see how we calculate the error. We say that, oh, the output, expected output should be this, but we got something different. We got, these are our outputs we received, right? So this is 0.77955, where it should be close to 0.95. And so how we calculate the error? The total error, which is also known as the cost function or the cost. So this is basically error of the originated by this one and error originated by this one added up, summed up, okay. uy1, error of y1 and error of y2. Now this is the generic formula is sum of half times expected minus actual, okay, expected outcome minus actual outcome whole square. This half is basically a constant being brought because when we partially differentiate this this formula, the square will come out and half will be cancelled. So that is the basic objective. Otherwise the half has no separate meaning, or it does not really affect the computation in any way. So now you see, if we put this uy1 and uy2 and to calculate, we'll find the expected for y1 is 0.05 and minus the actual is 0.73, and then we do the square, and similarly we do for the other one. And for y2 the expected is 0.95 and the actual is this, so we put them and we calculated, and the error is coming to be 0.24908. That's the total error, okay, total error of this neural network. Now you see, as we have seen that the error function, if we plot the error with respect to any w, any of the weights, there are so many, 8 different weights, and if we plot with any particular weight, we will see the function is basically a convex function. It's a square, it's a parabolic curve, okay, it's a convex function, and it is something like this, okay, not exactly this, is just an example one, and we have seen that in the gradient descent that this reduces, and this is probably the best point where the error is reduced, okay, or the minimum. So so this part of the slope is a negative slope, it's reducing, and this part of the slope is again going up, so positive slope. So from the gradient descent algorithm, we know that if we want to calculate the new value of w, update that particular weight so that the total error goes towards 0. That means this is the output has some error. We say, okay, can we go back and tweak or tune this weight little bit so that our error is less, and we will do this hit and trial, tweaking, increasing it, decreasing at times, and see that how we can go towards the minimum using the gradient descent algorithm. You see the W new, the standard formula, the new weight should be the old weight minus alpha times the del E times del E by del weight old. That means this is the we differentiate, calculate partial differentiation, and then what is this? This is nothing but the slope of that curve. This is the first order derivative, is nothing but giving the slope of the curve, okay. So if let's say our predicted value or the actual value is here, and the expected value, the minimum is here, so we will see we have to come down and reduce the weight. So what we do, we take the derivative at different points and keep reducing. So when we take the derivative, this is the learning rate, alpha is the learning rate, and then what we do, so if you see that this item will be negative, okay, if the negative slope, this will be negative. So if this is negative, then this negative times negative will be positive. So that means this will be added up, okay. So the new weight will be more than the old weight, right? New weight will be more than the old weight because the slope is negative this side. You see, that means if we move this side, W is increasing, then only we are going close to the minimum. That means W new will be higher than the W old. Now if we start from there and we reduce little bit, then again we reduce little more, then let's say we reduce too much and we kind of go to that side. Okay, so then we'll find, oh, now the slope is positive and it's kind of there is still pretty large gap from the minimum. Then we'll again come back from this side to this side. That time it will be reduced. Okay, the slope will be positive, means this will be reduced. W nu will be less than that W old, and in that way we can do few times, zigzag, and then finally drop onto the minimum. That means when the expected value and the actual value are very, 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 very close, then we stop the repetition. And we do it, this is just for one particular W. You see, this kind of graph is possible for all the 8 Ws. And for a large neural network, there can be many, many weights, thousands of weights. There will be many hidden layers, and each hidden layer can have many neurons. One thing I want to tell you here, that hidden layers can, it's not necessary they have equal number, like there are 2 hidden layers, both have 2 neurons. It's not necessary. One can have 10, another can have 2. It's possible, okay? So, and there will be many associated weights. So we have to tweak every weight, and then first tweak, let's say W prime 1, 1, so which is that closest to this output, and then this one, then this one, then this one. Then we can go back to this weights before the hidden layer and then change them as well. And then again, when we have tweaked all the weights, then again we'll do the forward pass or forward propagation to see whether the output has changed or not. Is the output now close to the expected one? And that means the error should reduce. So this way, every time we can do the same thing. Forward pass goes that direction, backward pass comes back, changes the weight, and again does the forward pass to check the weight has changed or not. In this way, over time, the weight will reduce, will become minimum, and that might take like 1,000 iterations or 10,000 iterations. But finally, neural network will find the best function to optimize or to track the training data, and that's why neural network is so powerful. And we'll see some example of backward propagation using this same network in the following video.